I've talked about how we can use the ideas from gravitation to calculate potential energy for electric forces. And we've also seen that the formulae for the potential energies are similar in that both have a 1 over r factor in the formula, and the rest are terms that do not depend on the distance r. Now we know from earlier examples, earlier videos on gravitational potential energy, that we can use the change in potential energy, for example, as a body falls in a gravitational field, to calculate the kinetic energy gain of the body. Now, in the same way, we can do it for a charged body under the attraction of an electric field. So let me try and do that for this example. In the case of the gravitational field, we will do it by, say, when a ball falls from here to there, all we need to do is to find the potential energies at the starting and the final position and take the difference. And the fall in the decrease in potential energy would then be the kinetic energy gained by the body. Now let's try that for the electrical force. So first, I'm going to suppose that there is a charged object starting from a bit further. Let's say this charged object of 0.0001 coulomb, let's say it was initially here. I'll call that position A, and I'll call this position B. So suppose that it started there from rest, and then when I let it go, the attraction by the positive charge would attract this body and pull it in this direction. What I want to do now is to calculate the speed when it reaches here. So let's see. So it starts from rest. So it was there. It started from rest. And suppose that this distance, additional distance here of 1 meter. So it falls over, it moves, it gets attracted by the positive charge and moved over a distance of 1 meter. And we want to now find what is the velocity when it is at this position. So the plan, as I've described, is to find the potential energy here and here, and then say that the difference is equal to the kinetic energy. Right, so let's try that. Starting at position A. Now at position A, I want to find the potential energies. I'm just going to use PE, right? PE as a short form for potential energy. Okay, and I'm going to use the symbol U to represent potential energy, and for the value at the point A, I'm going to use a subscript A to remind myself that this is the potential energy at A. Okay, and to find a value for this, I would use the formula for potential energy, which we've seen just now. I'm taking this charge as big Q. I represent the smaller charge, which is this value here, by small q, and the formula is charge times charge divided by 4 pi epsilon naught times r. That's we need a minus sign here. Remember that as for gravitational field, minus sign means that the force is attractive. Okay, so using this formula, you can now calculate an answer. How would this look like? The minus sign here. Now the big Q there is 0.001. So 0.001 times small q is 0.0001, 3 zeros, okay, divided by 4 times pi times epsilon naught is 8.85 times 10 to the power of minus 12. And r, the distance at A, is 1 plus 2. That's 3 meters. Okay, and with this and my calculator, I find that the answer is minus 298 joules. And joules is the unit for energy. So in the same way, I can then find the potential energy at B. At B, I'll let the potential energy be U with the subscript B to remind ourselves that I'm talking about position B, and I would use the same formula as before, except that this time the charges have not changed, but the distance, instead of the 3 meters for A, is now 2 meters from B to the bigger charge. So that's 2 meters, which means that I need to do the same calculation, except that I must change the 3 to the 2. So I would carry out the same calculation, a similar calculation, and then when I do that, right, with the 3 changed to 2, I'll find that the answer is minus 447 joules. So these are the potential energies at A and B. Now you can see that the potential energy at B is lower, it's more negative than the potential energy at A. It's more negative. Okay, and this suggests to us that that an object would tend to fall towards a place that has lower potential, because then there would be a decrease in the potential energy, and then it can gain kinetic energy. So that's one way to think about potential energy. All right. Now let's calculate this decrease in the potential energy. Now we know that this decrease has to change into kinetic energy, because it can't just be destroyed, and there's no other types of energy involved in this example. So the only other type of energy that's possible at the moment is the kinetic energy. Now I'm going to represent that by, say, E K for kinetic energy. So that's my kinetic energy when it's fallen from A to B. So I must take let's see, this is bigger than this. Alright, so that the potential energy at A is bigger than the potential energy at B. So when it falls from A to B, there's a decrease in the potential energy. And to find the decrease, I must take the potential energy at A and minus away the potential energy at B. So I must do UA from up there minus the UB from here. That means that I must take this number and minus this number. Okay, and when I do that, I find 149 joules. That's the kinetic energy gained. So as this smaller charge falls from A to B under the electric force, it will go faster and faster, and when it reaches B, when it has reached B, this would be the value of its kinetic energy. Now, I really wanted to find the velocity at B. So now that we know the kinetic energy, we can find the velocity. We know that the relation is half mv squared is equal to kinetic energy. So I can rearrange this. I move the 2 over, divide both sides by m. I'm left with v squared. If I then take the square root of that, I should find v. We already know the kinetic energy, which is 149 joules. The mass of this, so we also need to know the mass of this object, which I have not given. So let me say that, okay, this is just a small object. So let me say that the mass is just 1 gram. Just 1 gram mass. So if I now substitute it into the two values into here, let's see what we expect to get. Get the square root here, and 2 times EK is 149, and the mass there is 1 gram. We need to convert to SI units. That would be 0.001 kilogram. And with this, I can use my calculator, and the answer I found was 546 meters per second, faster than the speed of sound. So mustn't forget that this 0.001 coulomb is a very big charge by everyday standard.